Record. Okay. Google Form, here are a couple of questions for you. A, what force does electric field E exert on a charge? B, so give me the force in terms of electric field. What voltage does E create? Give me the formula for voltage that links voltage and field. C, what, that is a W that I should not write that. What force does magnetic field exert? D, which direction would an electron moving up in an into page B field be force, expansive force, field force? One more on the force direction. I think this is important. Excuse me. God, I hope I did not catch that daycare sick. Don't look at your notes for these. I want to see what you actually know, what you've learned, what you remember. If you do look at your notes, stop. If you were looking at your notes, stop to answer these. Tell me what's in your brains. And then look at your notes before I give the answer. Photon? God's sake. Proton is moving eastward. Which direction does that feel a force? What? 4 minutes to answer these? Do these individually, put them in the Google form, and then please turn to your neighbor and argue about them, okay? Check each other. Where's that go? God's sake. Solve for force in 1 and 3, please. So velocity is up. The magnetic field points into the page. Which direction is the force? There is no F. What you talking about, foo? There is no F. No people answering F. More than one. Gesundheit. Okay, one more minute. Give me your best shot. Hmm. Okay, I'm looking for formulas for A, B, and C, by the way. Tell me the formula. And time's up. All right, I am muy pleased about A and B. I think more of you got A right than you did on the midterm one, even though we haven't been using this bunch. The electric force formula is Q times E. Write this down. The magnetic force formula is QVB. Sine theta if you're into trig. The relationship between voltage and electric field, properly change in voltage, equals properly negative E times change in position. What I'm looking for is F equals EX or F equals ED. Right, and I have to reason through these. Okay. Electron moves up, V is up, B is into page, V cross B is left, electron right. Very few people got that. I think we need to review the right-hand rule. Proton moving east, I'm going to pretend this way is north so that I can reason about this. B is north, V is east. For V cross B is up, and it's a proton, so force is up. Okay, so what I'm seeing is I don't need to review the first two. The third QVB, I'm going to give that to you. We did not do magnetism for very long at all. If you forgot that, okay. There you go, write it down. F equals QVB. Remember, the right-hand rule, though, is the big thing we need to review. First off, the stupid mnemonic, stupid, slightly vulgar mnemonic. Hold out your hand, your right hand, palm up. You're getting a gift from your aunt, but your aunt gave you a sucky gift, so flip her off. Then go hitchhiking with your thumb. All right? Freeze those fingers. You can move your arm, you can move your wrist, but you can't change the orientation of your fingers, okay? Now, once you've got your fingers frozen, you align them. V is your first finger. V is the first letter with the direction. B is the second finger, the second letter, V, B. Do the Q part later. So first finger V, second finger B, align them in whatever orientation I'm saying. And then your thumb is the resultant of VB, V cross B. If it's Q is a negative, negative thumb is the opposite sense. Who wants more examples with that to practice? You guys okay with this? One more example. What's out, cross up? First page, out. First finger, out. The point behind you. Cross up. Middle finger up. Out, cross up is, which direction would you call this? From your perspective, that's left. Remember, out is not out of you. Oh, for dog's sake, it's left. I'm sorry. I did the exact same mistake that I was going to point out for you. Out of page is towards you. Your left. No, you don't like that. Out of page is towards your face, but I don't care about you. I care about the page. I care about you. Yeah? You're going to need that for what's coming. But I'll practice it as we go, too. Okay, so with the note that I'm going to definitely go slowly and surely on right-hand rule, let's dive into this. There is a phenomenon that you have not yet learned about called motional EMF, and this underlies this and related physics underlies what makes the lights run in this room. That is to say, what makes the entire darn city run. The source of electricity generated by power plants, everything except for solar power, Palo Verde nuclear power plant generates electricity this way, is motional and Faraday EMF. Hey, by the way, what does EMF refer to? Anyone remember EMF? Electromotive force? EMF is another name for one quantity. Voltage. When I say EMF, think voltage. Okay, so if you shake a conductor around, the charges, the pluses and the minuses on it, are moving in a magnetic field. You don't have to just do this with an isolated test charge, like a Q moving at speed v. You could do this with a whole conductor full of charges. And very importantly, if you have a piece of metal moving in some direction, the V is the same for the pluses and minuses, the B is the same for the pluses and minuses, but the Q's are opposite. So what does that tell us? The force on the plus charges, the protons, the nuclei, is going to experience an opposite direction as the force on the electrons in the sample. So what happens? If you move a test charge, if you move a single charged object in a magnetic field, you feel a net force. If you move a conductor in a magnetic field, you don't get a net force. There's equal and opposite amounts of force on the electrons as on the nuclei, but you are going to get the plus charges move to one side and the minus charges to move to the other side. You'll get a voltage across that. Our goal now is to come up with a formula based on what you have already learned, stuff you already understand. We're going to come up with a formula for that voltage. Okay, so magnetic force pushes opposite Q's in opposite directions of F. And here is the idea for how to figure out the voltage. Flow will continue up until the point that the electrical attraction between the two separated charges balances the magnetic repulsion. That is to say, there is a magnetic force pushing pluses one way and minuses another way, pushing them apart. They will reach the ends of the rod and you'll get a plus side and a minus side of the rod, but they are still electrically attracted to each other. They are magnetically pushed apart, but they are still electrically opposite charges attract. Yeah? All we're going to do is we're going to set those two forces equal to each other. So we've got the force formula QE. We've got the force formula QVB. Can you tell me the value of E that you will get when these forces are equal? Do this. Question, what are we at? E in the Google Forum. F in the Google Forum. Give me an algebraic expression for the electric field when these forces are balanced. This should not take you long. Simplify. Okay, as most of you have realized, if QE equals QVB, QE equals QVB, I can cancel Q on either side. The electrical charge and the charge which feels a magnetic force are equal, the same charges. So I can write E equals V times B. What is this electric field? This is not the electric field from magnetism. This is the electric field resulting inside the material because the charges are pushed apart inside the material. So again, this only happens when you move a conductor in a magnetic field. The magnetic force pushes them apart. It pushes them far enough apart, enough of them far enough apart to create this electric field. When this electric field is formed inside the material, then you'll get a balance and no more charge will flow. Again, electric and magnetic forces are balanced. Okay, now follow-up question, how much voltage is there? Electric field is hard to measure in a material. Voltage is trivially easy. $5 multimeter measures voltage pretty accurately. How much voltage is from one side of the material to the other? What's the voltage formula? VED. So using that great, fantastic principle of algebraic substitution, I could write VBD. Now, be careful, write this down. This is important, this is central. Be careful to identify your variables. What's this V mean? Voltage, what's this V mean? What's this B mean? What's this D mean? Yes, good. You got it. Yeah. Velocity. From QVB, what's the V in QVB? That's where he comes from, velocity. Now, I want to emphasize a couple of things. The direction that the charges separate can be figured out with the right-hand rule. That's the dimension, the direction, the D that you care about, okay? So if the magnetic force is separating charges up and down, I don't give a crap about the width of the bar. I don't care about the depth of the bar. I only care about the height of the bar. You have to use the appropriate dimension in the problem. Think about which way are the charges being pushed apart. Use the right-hand rule. Work out which axis those are. That's D. That's good? Sometimes you also see this written L. D, L, H. I don't care. The direction perpendicular to velocity and field is the important direction. Actually, I think at the very next slide I write L. Whatever. The distance perpendicular that the charges move along that axis. Okay, it sucks to have V equals V something, right? However, there is a traditional substitution that we can use. You may even see in your textbook when we're talking about voltage sources. This is the common alternate notation. When talking about voltage sources, batteries, wall outlets, motional EMFs, we will write a script, a cursive E instead of a capital V for voltage. So you will also see written script E equals VBD. I want to emphasize this is not electric field. This is an alternate notation for voltage, okay? E for EMF, not E for electric field. Follow along? Then at least you don't have to have V equals V something. You don't have to make sure to write voltage and velocity so differently. Now, there's a deep and profound and important law that we're going to discover. And I want to get into this in a second. What we're going to, sorry, hold on, step back. Great, there's a voltage across the bar, so what? This voltage is real. It is a real energy source. The magnetic field is exerting a force pushing the charges this way and that way. You could use this like a battery if you've got the bar moving in the magnetic field and you attach them to a circuit. This will drive currents, charges, this will drive a current in a circuit. Now, usually we don't hold up an entire electronic device The canonical example that I will give you questions about goes as follows. You make a U-shaped wire. The wire is all about you. I'll have a good swing. Here's a U-shaped wire. This wire carries some resistance. We usually say there's R resistance, R ohms of resistance in this, whatever. And oh, I said the moving bar is on top. Sorry. Let me draw it according to what I said in the, how I described it in the picture. Okay, so I've got a U-shaped wire, and the moving bar is the thing that's going to have that motional EMF in it. So I've got a bare wire, rawr, not that kind of bare, a bare wire with a piece of metal, a conductor, that is touching the wire. It forms a complete closed circle, rectangle, except the top bar is free to move up and down. Now, the terms that I gave here, we're going to invent an equation in 2 shakes of a lamb's tail and call this H. I call this length of the bar as L. And the voltage due to the field drives the current. Let's find the current in the wire. I told you before that we're going to say that the wire has some resistance here. There's R ohms of resistance in the wire. Tell me a mathematical expression. Question, oh God, what are we on? G, question G. Give me an algebraic expression. If you move the bar at velocity V in a magnetic field B, given this geometry, how much voltage appears in, how much current appears in this circuit, in the wire? There's a magnetic field here. I'm going to take the bar and I'm going to drag him up along the long rails at speed V. How much current do you get? Put your pieces together. You got all the pieces you need to make this. I mean, current that flows. Oh, you guys are guessing. Use the formulas, Luke. Did we not just find a formula for the voltage induced? If we've got the voltage and I tell you that the wire has some resistance, what gives us the current? What formula is going to encourage current, voltage, and resistance, eh? What's the formula for the voltage in this case? Well, we just write down. B. In this case, what's the direction that I care about? The bar is moving up and down. Its velocity is up and down. Right hand rule. Velocity up and down. Magnetic field, as I just drew up there, into the page. Which direction is the charge being pushed in this bar? Left, right. So which direction is the relevant distance? The width, the left-right distance of the bar. L. I give you current. I give you voltage. How do you find current? There you go. There's several homework problems. But let me encourage you. Don't memorize every formula you see. You don't got brain space for that. I don't got brain space for that. And ain't nobody got time for that. Look, what do you need to know? You do need to memorize. Here is a new equation that you need to know. The voltage induced in a moving conductor is the velocity, the magnetic field, and the perpendicular distance multiplied together. VBL, VBD, VBH, whatever the distance, whatever direction that distance is. Here? Yes. When it's a voltage source. If we were talking about the voltage lost in the resistor, a voltage stored in a capacitor, the voltage dissipated in a circuit, I use capital V. When it's an energy source, the energy is coming from here. Script E is very common to use. Just don't get it confused with electric field. Yeah, is good, is good. Again, I want to emphasize the moving rod behaves like a battery. An uncharged rod with no chemical reaction stored inside it is able to transform energy from magnetic form into electrical form. And ultimately that gets dissipated in thermal form. Okay, let's do numbers. We've written lots of letters. Give me a number. Give me your number. Kristen H. Oh, you can help each other. Talk now, talk now, talk now. Now's the time for you to talk. Check your units, peeps. A lot of silly mistakes here. Well, a lot of people making one silly mistake. Hey, one more minute. Okay, time's up. 0.8 volts. 0.806 volts. Full precision. How do we get this? New formula, BLV. Be careful. I tell you 32 centimeters. What's the SI unit for distance? I had a number of people tell me 81 volts. Watch out. Okay, let's suppose that the wire has, I don't know, 15 milliohms of resistance. Can you tell me the current that flows in the wire? 15 milliohms. I'll say R. So question I. Nah, 150. 150 milliohms. 15 milliohms is really low. So we're going to connect this to a U-shaped piece of wire. move it? How much current does it drive? All right, good. V equals IR, 5.5 amps, 5.4 amps. Many people got that. You good? How do you feel with this? Okay, now, as I was starting to say a moment ago, I was jumping the slide, jumping the gun. No guns, jumping the slide. There is another way to write this that ends up generalizing and explaining other phenomena even when nothing is moving at all. And it's kind of spooky, kind of creepy that the same formula can explain like 5 different phenomena, even though they're different phenomena. In fact, the fact is this coincidence is one of the things that drove Einstein to figure out the whole theory connecting space-time and speed of light and time dilation and length contraction, all that stuff. But that is beyond the scope of the class. What I am going to say is that I'm going to introduce a new term, define phi magnetic flux encompasses just how much total magnetic field you have in a region. It is the product of field and area. And in particular, we're going to look at the area being surrounded by wire. The area is the area subtended by some wire loop or loops. Phi is the dot product of B times area. B a sine theta if you're, B a cos theta if you're good at trig. I want to emphasize the magnetic field must be perpendicular to the area. Oh, perpendicular to area, which direction does area point? Area is a plane. If you are perpendicular to the plane, you are at right angles, you are not in the plane. So if the area is the area of my hand, and the magnetic field is, to the right or left, then this is not perpendicular. The flux would be 0. If the magnetic field is pointing up and my hand is up, down, left, right, then that is not perpendicular. If my hand is up, down, left, right, and the magnetic field is pointing in, out, that is perpendicular. Okay with that? The magnetic field must pierce the area in general. Okay. What can we write as a formula for how magnetic flux changes? As we will discover, the master formula for understanding all these different phenomena involves how magnetic flux changes. Just because you have a magnetic field, just because you have an area it covers does not mean that you've got an electrical phenomenon. What happens is the magnetic field changes. In the previous example, what were we changing? Were we changing the magnitude of field? Were we changing the area covered by the wire, the area surrounded by wire? Yes. Right? We had a loop of we had a U-shaped channel of initial height h and velocity v and width L, right? What's the area? What's the initial area of this? I got a rectangle of height h and width L. LH. Now here's the thing. H is going to change. This is going up at speed v. Can anyone tell me an equation last semester that tells me how high the bar is at any time? Yes, you can. Your formula should give you h when time equals 0, and your formula should have the height changing by v meters per second. Distance equals rate times time, peeps. Where does that go? I challenge you. I challenge you. Can you give me a formula for height as a function of time? This will be question J. I challenge you to give me a formula for height as a function of time. Gesundheit. Okay, so my question again is I've got a rectangle that is L wide. The channel, the U-shaped piece of wire is L wide, and the bar starts out h above the bottom. We start out with an initial height h. I want to know if the bar moves up at speed v, where is the bar at any given time? Starts at h, moves with speed v. Give me a formula for discovering the height as a function of time. Hint, hint, hint. We define velocity as the rate of change of a position. In this case, I care about vertical velocity, so I care about vertical position. Hint, 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 hint. There is no acceleration. It was at steady speed v. What is velocity? What does velocity mean? What does it tell us? Change in position divided by change in time? Yeah? Displacement per time interval? Delta y over delta t if we're talking about vertical direction. What does delta symbol tell us? Change, final minus initial. So I could rewrite this as final minus initial equals vt. Can I solve for v final? Y final? So a position in the vertical direction could be told if you tell me where it starts plus its speed times how long time has progressed. Hint, 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 hint. What did I ask for? I asked for the height of the bar as a function of time. 1 minute. You could do this. I've walked you 95% of the way there. Okay, so here we go. I wish to take this formula, which is really just the rewritten definition of velocity, and plug in. I want to know how high the bar is, the y position of the bar. The height as a function of time formula is where does the bar start out? It starts h above the ground. How fast does it move? It moves at speed v times how long have I talked about t? There we go, I just plug in. Challenge I gave was to find a formula for the height as a function of time, h plus vt. I've driven all of last semester out of your brains. Eh? No? Okay. Okay. So where I'm going with this, because there is a purpose for this, is I want to find a formula for magnetic field times area. I want to find a formula for flux. Find a formula for flux. Magnetic field, that's just a constant, right? What's the area if I've got a changing height? If height is a function, can I re-express this in terms of this formula? Look, what's the area surrounded by bar and 3 wires? It's always length times height, right? Yeah, everyone sees even if h changes. So I can write let me give you numbers. Many of you are vastly more comfortable with numbers. I've given you almost all the numbers. Let's say h, the initial height of the bar is 10 centimeters. I don't know. H equals 10 centimeters. Give me a formula. Plug in, get numbers, be happier. Give me a formula for the flux as a function of time. I'm not telling you a time yet. I want a formula. Simplify the formula too. This is question K. Plug in numbers. Give me a formula. Simplify it. Okay, I give you B, I give you L, I give you H. I give you V. Plug in and simplify. You can do this. How's it coming along? How's it coming? Okay, my friends, I've given you numbers. I've given you formula. Plug the numbers into the formula and simplify. That's all. That's all I'm asking for right here. I'm trying to bring this formula back to Earth so that we don't have so many letters. Question. 10 centimeters. The y offset. Y-intercept. Okay, I don't want to spend all day on one calculation. Let's bring it together. What I'm looking for when you plug in is you get 0.013 plus 0.8060. 0.806? That number sounds familiar. You remember when we got 0.8 something just a moment ago? What is this? This is the voltage. Voltage is just, what is 0.806? What is its role in this equation? Constant plus constant times time. What are these? Y equals B plus mx. Yeah, it's the slope. What is this called, by the way? 0.013 is this is slope. This is your independent variable. Your y offset, y intercept. Deja vu? Okay, this is unimportant physically. This is just your initial flux, and the actual initial flux doesn't change anything in the problem. The new law that we have discovered, uncovered, that I'm driving towards, is that the slope of the flux, the rate of change of flux, delta phi divided by delta t, is how you could calculate induced voltage. And that ends up applying even if you don't have an area which is changing because of a velocity of one end of it. So here is our new and final super Saiyan form. Induced voltage can always be calculated using the formula, the rate at which phi changes, the change in phi divided by the change in time. Yeah, change in flux per second, per time. Okay, so this involved algebra at 5:30 p.m. And I get the feeling that y'all aren't happy about this. Please turn to your neighbor and spend dose minutes discussing what the heck just happened. Where did these numbers come from? What do the letters mean? What is our punchline? 2 minutes. David, it's not the worst date to be late to the class. We started with one new formula, BLV. Voltage is BLV. Yeah, this is an alternate way of writing voltage. Script E is voltage when you've got voltage source. So how I came up with this formula is to say if I could write flux as a function, I can say how is flux changing with time? What does it mean to have a change in flux per time? That's just slope. It's not phi divided by t. It is the rate at which phi is changing. Delta phi divided by delta t. That's what slope is. Y over x? No, delta y over delta x. It is a measure of total amount of magnetic field. Magnetic field times area. If you've got a small magnet, you might have a strong magnetic field, but it's not making a magnetic field over a very wide area, right? The Earth's magnetic field is quite weak, 52 microtesla, but it's a very huge region of space. The Earth's flux is actually quite big. You could visualize it as a count of the number of arrows. Magnetic field strength itself would be the density of the arrows, how compact, how bunched up the arrows are. That's the Teslas. And the number of field lines, that's flux. Total number of flux. I'm always going to give you constant fields in here, steady, uniform fields. Give me a question. Where did I lose you? I know I lost half of you, at least. Tried to build up to this. Tell me where. Say that again? Uh-huh. H plus VT as an addition. I just multiplied BL times H plus BL times VT. Okay. My goal in walking through this was this isn't exactly a proof, but I was trying to get you towards realizing where this comes from. This is not new physics. This is a restatement of our formula, BLV. But the magic is, as I hinted before, this formula is actually more general. And this will apply when you don't have your bar moving with a speed v. This can happen when your magnetic field changes. This can happen when the other direction expands or contracts. The voltage is actually a very real electric field circulating in space that pushes charges around a loop of wire, and that comes into existence anytime you have a changing flux. If you can find the rate at which the flux changes, the slope of the flux versus time, you know how much voltage is in that region of space. That's the punchline. That's what I was hoping to drive towards. Questions on this? I will not make you do the derivation on the quiz or the exam. You will be expected to be able to, if I tell you a flux function, recognize its the induced voltage part of it. Let me give you another problem. Let me give you another example. Suppose this 0.42 Tesla is not actually from a a uniform field everywhere. Say I just have the magnetic field, excuse me. Say the magnetic field is just confined to the left side of this page. And instead of having a U-shaped channel with a bar of wire, I'm going to take a hula hoop. Here's a hula hoop of radius. How big is a hula hoop? Meter across? Let's say 80 centimeters. Be careful, this R is not resistance. The hula hoop is of wire. Plastic won't feel a current flowing through it. Oh, I've also got to give you the resistance. I'll use the resistance up here. R is 0.15 ohms. So the resistance of the loop, 0.15 ohms. The radius of the loop is 0.8 meters. This is something where you're not going to get a direct formula. This is beyond your level to get the formula for flux as a function of time. But I challenge you, can you reason about the formula we've got and tell me the average voltage as I drag the hula hoop from the field region to the no field region? I will tell you, I'm going to change the velocity. Nah, not 1.6, 3.2, 3.2. Hey, how wide was the diameter of the loop? 1.6 meters. What's the speed? 3.2 meters per second. How long does it take the loop to exit? Could you find the time it takes 1.6 meters of material to move at 3.2 meters per second? Half a second. Can you find how much the flux changes? Here I've got a full area's worth of flux. Here I've got zero flux. Can you find the average flux per time as this is dragged out? Try it. Give it a shot. Work with your classmates. I fear that it is also late in the day. You did an hour and a half of Morse and your head hurts? It should not be wired like that. I should have wired them so that they're in parallel. No, this is the paddles. That's connected to the paddles. That's the headphones, but the headphones aren't in stereo. Yeah, that's very annoying. I thought the circuit I designed would put them in parallel. I'm sorry. Good. Have a D. What are you practicing on? What are you practicing with? Just sending it. Sending it. Of course, of course. Good. Good, 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 good. Good. I'm looking for a number, by the way, of voltage induced, the average voltage as I change the flux from whatever it starts at to zero. Hint, 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 hint. Question. There is no H here. To just plug into the previous equation, think about what the terms mean. What does it mean to change flux? Hint, 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 hint. Magnetic field is 0.42 Teslas, by the way, right up there. Good, Sammy. That's right. Good, Ethan. Sarah, you got it. Delilah, you too. Good job. Taylor. David, who wasn't here for most of the lecture, got it. Good job. Good job. Okay, here's how I suggest you do this. By how much does flux change? You don't have a formula this time for phi. You know, just pattern match. You have to think about what change means, average rate of change. How much does it change by? How long does it take to change by it? Well, I think how much does it change by? It goes from an initial BA. Remember the area of a circle, pi r squared, ends at 0. So what I would do is delta phi on average is b pi r squared. Over delta t, how long does it take to move 1.8 meters to get completely out of the field at 3.2 meters per second? Distance over speed is time, right? In each second, you go 3.2 meters, so it only takes half a second to get 1.6 meters. Final answer is 1.7-ish volts. The sense of the voltage needs a more advanced law we'll get to next time. The direction of the voltage we'll get to. And it'll actually end up being not plus and minus, but clockwise or counterclockwise. The circulating voltage. Okay, I'm seeing some struggles here, especially in the kinematics part. That's not super central. I wanted to make connections, but I'm only slightly brokenhearted there. That I'm not going to test on. Next class, we're going to push through, and I think we can get into the more interesting applications of this, see what else this law could do, and maybe even, I am not sure, but I'm going to prepare for lens, and we'll see if we can get to lens. Lens is interesting physics. If you got that, if you get lens, you really learn something. It's a logic teaser. Okay, but anyway, we are done for today. Thank you for being here. See you next class.